With all those pieces that we have covered, sample space, events, axioms or probabilities, and those propositions, we're finally ready to talk about sample spaces with equally likely outcomes, which is going to be a key to our evaluation calculation of probability coming up. Okay, so notice that we're talking about sample spaces. Okay, we use that capital S, right? But here we are focusing on equally likely outcomes, meaning that any of the outcome, okay, each of the outcome, I should say, will have the same chance of happening. So to formally define it, suppose the sample space S has n, capital N, number of equally likely outcomes, okay, 1 through n, okay? So then, also I should say that the S, again, is the union of all of them, okay? Then because of the disjointness, because they are like union, meaning that, well, disjoint meaning that there is no intersection between any of the outcomes, okay? So because of that, we can use axiom number 2, I guess. Yeah, number 2 and 3, like total 1 as well as the countable addition. We're able to show that, well, the probability of the sample space, we know that's total 1, right? And then because all of the equally likely outcomes are disjoint, so the union of all of them, okay, it's going to be the probability of like the sum of all of the individual probabilities. But again, remember they're equally likely, okay? So they can be re-expressed as n times the probability of any event, which is the same across the board, okay? Once we have gone to this part, then we can actually write that the probability of any event, any outcome, let me just say it clearly, any outcome I going to be 1 over n. Okay, so that's when you have sample space S with capital N number of equally likely outcomes. And we actually arrived at this point doing the axiom 1, 2, 3, I think all of them. Okay, all right, so with that at hand, really useful, because then if we actually are working on an event E in a sample space with equally likely outcomes, then the probability of this event actually can be reduced to counting the number of elements in the set E over the number of elements in set S. Okay, so the reason we can do it again is because the sample space S has equally likely outcomes. Okay, because of that, then if I count how many elements, like in our case is capital N, right, in the denominator, in the numerator, we just need to find out the number of elements in that particular set, which is our event E, which is what we define cardinality. So if you see this pound sign that represent cardinality is the number of elements in set E, then we're able to get the probability of event E pretty directly. Okay, so again, keep in mind that this only works if you have equally likely outcomes. But again, this is very commonly done in many scenarios anyways. And also I would say is this one to think about when you have equally likely outcomes. So we are starting with this one. All right, let's look at some examples. Rolling, the probability of rolling an even number with a 6-sided die. Okay, so the sample space, we know that from early on. Okay. And moreover, each one, if it's a fair 6-sided die, each one is equally likely, right? So, and capital N here is 6. Okay. All right, let's look at our event. Event is getting an even number. Okay, so what are the outcomes? We can get 2, we can get 4, we can get 6, right? So cardinality of E, based on what we defined before, is the number of elements, which is going to be 3. Okay. So if we follow our results, the probability of E gonna be the cardinality of E, right, over the cardinality of S, which is 3 over 6, which is 1 over 2. Right? So this is formally, now you can see that, well, even I guess before I do all of the math expression here, you know that, well, if it's a fair 6-sided die, well, the chance of getting an even number is 1 over 2, okay, it's half, okay, because you have half of the numbers or even half of the numbers are odd. But then now, because we can actually formally define that this is a sample space with equally likely outcomes, and then we're able to do this cardinality computation, in the end, we're able to formally define and derive that the probability of event E is 1 over 2. Okay, good. And the next one is a couple has 2 kids. What is the probability that they're not both girls? Okay, 2 kids. not both girls. And I guess let me just also just define that. Let's just assume that it's boys and girls. Okay, only two outcomes here. Okay, so sample space is what? BB, okay, two boys, okay. GG, two girls. GB, okay, first girl and then second boy, and then BG. Okay, well, there are four. Okay, now we know that the denominator is going to be 4. The cardinality of S is 4. What about this event? Not both girls. Okay, so I can get two boys. Okay, I can get one boy, one girl. Okay, and one girl, one boy in that order, and then one girl, one boy, one girl. Okay, so if I do that, PE will do cardinality of E over cardinality of S, which is 3/4. Okay, so, well, yeah, that's the answer. But I would just also mention that in this case, even though we didn't explicitly say that, it actually matters in terms of the order of the two kids, right? Because you can have first girl, second boy, or first boy, second girl. Then actually it affects how we actually list the S and list E as well. Okay, so sometimes it's easy to make the mistake that, okay, well, I only have BB, GG, and GB, right? However, in this particular case, in this context, well, like the order of the gender when you have the kids matters in terms of, well, it's a permutation really, right? So don't forget that it could have two outcomes, GB and BG. So when you're doing that, hopefully everything starts to make sense. All right, the last example I want to cover so that you're able to work on some exercises later is the birthday problem, okay? And that is actually one of the scenarios that I was asking you early on about thinking about probability, right? Like what is the chance that two students in this class share the same birthday, okay? So to get us started, okay, ignoring leap years, let's just say there are 365 days per year, and assume birthdays are equally likely to be any day of the year. Okay, so 1/365, but now you can imagine for any person. What is the chance of no tie? Okay, notice what we're asking here. No tie, okay, among n students. Okay, so, well, keep in mind that we do highlight that we do assume that birthday can happen equally likely on any day of the year. Okay, so the probability, or let's not do probably first, let's do the cardinality, okay? Let's do the cardinality first of birthdays of n people, okay? And each one, okay, each person has 365 number of choices, okay? And then we have n people, so it's gonna be raised to the power of n. Okay, that's actually whatever the sample space they're working with, okay? And the event we're considering here is that there's no match, okay, or no tie. So what that translates to, now let's think about it. Let's just say the first person, we can have 365 choices for this person, right? Once the selection is done for the first person's birthday, then the second birthday can only be, right, 364. And we keep doing this multiplication until we got to the nth person, which is going to be 365 minus n, but don't forget plus 1, okay? Just like this one, this is the second person, we do 365 minus 2, but plus 1, okay? So the probability of no match or no tie, just do no tie here. Now we know, okay? Because it's equally likely outcome, right? So the top will be no tie, the cardinality, like the number of ways to get that. And then in the denominator, it's gonna be birthday of whatever we have written up there, okay? So it's gonna be 365 times 364 times 365 minus n plus 1 over 365 factorial, okay? Oh, sorry, let me get it right. So 3 factorial, yeah, this is good, right? And one way to rewrite it, if you're like really motivated to do those factorial things, right? Then you can actually write 365 factorial over 365 minus n factorial 365 and to the power of n. Okay, well, this is really just for exercise. It doesn't really help us actually get that actual numbers per se, but this is the final expression. Okay, and we don't know how to evaluate yet, and we'll get to that later. But I do want to show you that if I were trying to plot it, okay, this is how this p probability, like probability of no match, going to look like. Okay, so the x-axis is, sorry, it's being not able to see its n. Okay, that's the number of people. Okay, y is the probability of no match. Okay, so if you look at that, well, actually our size is what? Let's just say 30. Okay, with 30 here, well, the probability of no match is actually like, let's just say like 25%. Well, 30%, let me say. Yeah, 30%-ish. Okay, so I don't know how that goes with your guess at the beginning. Okay, and this is now formally we're able to show that because we're assuming that birthdays are equally likely, then we're able to use that results, our results of sample spaces with equally likely outcomes to get the probability.